All right, good morning. My name is Thomas Zachariah. It's a pleasure to welcome all of you. So I just want to let you know that the lecture is being recorded for later viewing on YouTube. For those of you who are attending this lecture for the first time, just to give you a little bit of introduction about this lecture, the Eugene P. Wigner Distinguished Lecture Series in Science, Technology, and Policy was launched in November of 2013. It's organized by our corporate fellows. The goals are to invigorate scientific discovery, spur technical innovation, and initiate productive scientific policy discussion and debate. The lecture honors Eugene Wigner, the patron saint of Oak Ridge National Laboratory, who was a chemical engineer by training, a physicist by tradition and inclination. He received a Nobel Prize in Physics in 1963 for atomic theory and founded the field of nuclear engineering. He is a role model for coupling basic and applied work, which I think is a hallmark of this laboratory. So the translational research in that regard, there is a lot of synergy between our speakers' previous lab affiliations. Sandia and Oak Ridge both have this sort of heritage of having this and emphasis on translation research. Eugene Wigner also was the research director of Oak Ridge National Laboratory, called Clinton Labs back then from 1946 to 1947. Wigner played a pivotal role in initiating the Manhattan Project. He was among the first to realize the threat that we posed by Nazi Germany in developing a nuclear weapon, and so he remained deeply concerned about the dangers of nuclear war throughout his life. So today's lecture is on a topic that would have been of great interest to him. Our speaker today is Alton Romig, the Executive Officer of the National Academy of Engineering. As the Academy's Chief Operating Officer, Dr. Romig is responsible for its program, financial, and membership operations. Before joining the staff of the Academy, Dr. Romig spent nearly 30 years working in material science, engineering, and characterization. He joined Sandia National Laboratory as a member of the technical staff in 1979 after earning his bachelor's, master's, and PhD from Lehigh University. At Sandia, he carried out pioneering work in analytical electron microscopy and solid-state diffusion. He advanced through a series of R&D management positions and was appointed the Executive Vice President in 2005. He served as the Deputy Laboratories Director and Chief Operating Officer until 2010, when he transferred to Lockheed Martin's famous skunk works. As the Chief Skunk, he led the development of a number of new technologies and systems, many of them classified. He became the Executive Officer of the National Academy in March 2015. In recognition for his technical contribution, he has been awarded many distinguished medals. One is Burton Medal of the Electron Microscopy Society of America, ASM International Silver Medal for Outstanding Materials Research, and the ASM TMS Distinguished Lecture in Materials and Society. The National Materials Advancement Award, most recently in 2005, serves on numerous advisory councils and boards, and including the Intelligent Science Board, which provided independent scientific advices to the Director of National Intelligence, and the Board of Directors of the United Kingdom's Atomic Weapons Establishment. He is a Fellow of the American Association of the Advancement of Science, ASM International, and TMS. He was elected to the National Academy of Engineering in 2003 and to the Council of Foreign Relations in 2008. In his lecture today, Dr. Romig will discuss the National Academies and nuclear nonproliferation, yesterday, today, and tomorrow. Please join me in welcoming Dr. Romig.
Well, good morning, everyone. Is the mic on? Okay, good. It's a real delight and treat for me to be back in Oak Ridge. During the 80s and early 90s, I spent a great deal of time here, both at Ornell and also over at Y12. Back in those days, it was still all one contract for a few of you who were around back in those days. But it was like a chance to go back and relive part of my youth, to be able to come and spend a couple of days back here with you again. In fact, the last time that I was at Ornell was right about the time that the SNS was about to open, and Tom Mason was the project manager for it, and he was so proud of what was about to be turned on to become a real landmark of discovery, really globally, not just in the U.S. So what I plan to talk about today are the role that the national academies have had in the nuclear nonproliferation program for the U.S., going all the way back to the very beginning. And I thought what I would do is start a little bit just with what the national academies actually do. Many people have the sense that it's purely an honorific society, that people are elected either in sciences or engineering or medicine into their respective national academy, and that's really pretty much where it ends. But that's really not true. So what I pulled together here is a history that lays all this out, culminating in what it means for nonproliferation, what it meant going back many, many decades, and through today, and where I believe we're going in the future. And I certainly owe a real debt of gratitude to our historian, Daniel Barbiero, at the Academy, who helped me go through the archives and find these various bits of history. So first off, this is our start. In 1863, Abraham Lincoln created the National Academy of Sciences. Of course, the question is, why did he do that? Well, the issue that he had was that that was the birth of iron-bottom ships in the U.S. Navy. And there were issues with iron-bottom ships. One is they had corrosion, and two, how the heck do you make a magnetic compass work inside of an iron ship? So what Lincoln found, if he went to the Navy and asked them for the answer, it basically boiled down to, we'll give the Navy more money. It wasn't very satisfying. Then he went to the shipbuilders and the iron makers and said, what do I do about these problems? And it was basically, give us more money, we'll work on it. And he said, this isn't going to work. Everybody has a vested interest. I want something completely independent. And so he actually turned to a senator by the name of Henry Wilson, right here, from Massachusetts, who had been a key figure in the creation of the American Academy of Arts and Sciences up in Boston, to pull together an organization that later became known under congressional charter as the National Academy of Sciences. And its role, as you see there in red, is to investigate, examine, and report upon any subject of science or art to any department of government, and to do so without compensation. In other words, you're not going to get paid to do it, other than covering expenses. So I'm sure I know there are people at Oak Ridge, and there may well be people in this room who have sat and served on a variety of National Academy functions. Klaus, did we ever pay you to do anything? No, we don't. That's the whole premise by which we're created. The money that's raised will do things like buy airline tickets, it will pay for hotels, it will feed you, it'll pay for a building that you can actually do studies in, and it'll pay for a small staff to actually help manage the work. But otherwise, you don't get paid for it, the sense that there will be no conflict of interest. So we're unique in the world as academies that advise the government but are not on the government payroll. In fact, when you talk to another academy, oftentimes, even after an hour, you can't get it through their head that somebody in Congress doesn't write you a check just to exist. It doesn't. So I would say that when you talk about the academies, the independent variable is service to the country. The dependent variable is you need smart people to do that and knowledgeable people to do it. So we're going to elect people to our membership. And so yes, it's an honor to be elected. It means you're deemed to be one of the preeminent scientists, engineers, or medical professionals in the country, but you're really there because you were intended to serve the country and meet its needs, as I've just described. Well, after the Civil War, and by the way, this is what I would call a 1920 version of Photoshop. This actually never really happened. In 1920, when the main National Academy building was built, funded by Andrew Carnegie as a gift, they hired an artist to create what could have been or represented the founding in 1863. So this is an artist's vision of what it looked like. This is not really a photo of how it happened. In fact, Lincoln signed the document around 11:30 at night by a kerosene lantern in his office in the White House. It was not with great fanfare. Well, here's the first issue, the iron-bottom ships. And that happens to be a ship called the USS Cairo. I have no idea why that is its name. But, as I said, issues around corrosion and around magnetic compasses. If you read the first report about corrosion, it's 9 pages long, handwritten, and the conclusion is, heck if we know. They didn't know how to solve the problem. The second study on how do you make the magnetic compasses work in iron ships, that one actually had a solution. Rather complicated and tedious, but it had a solution. I think we all certainly know that magnetic and true north are deviated from one another. And if you look at a navigation map, there are these lines of deviation that show you at any position on the globe what the deviation is in compass reading between true north and magnetic north. So they took an iron ship, they put a magnetic compass in it, and they said, okay, that's going to create another deviation that will add to the deviation due to true versus magnetic north. And then they say, now we have to know about the direction to the ship. So they took a ship to a known landmark where they knew the directions from geographic references, and they drew a third set of curves that accounted for the orientation of the ship, right? And so it was a combination of those three deviations put together in tabular form that allowed them to compensate for the magnetic deviation due to the iron ship and its location and so forth on the globe. That's how that problem was solved. Well, things were relatively quiet for the academies, excuse me, until we got to about the approaching of World War I. And at that time, Woodrow Wilson signed an executive order creating what was called the National Research Council, which in fact still exists today. And it is meant to be the working arm of the Academy. Between the Civil War and 1916, there were probably only about a half a dozen times the Academy was asked to do something. It was done on a purely volunteer basis. I mean, there was no money paid at all other than to buy train tickets and probably food and hotel rooms, but there was no infrastructure to support. Well, when 1916 came along, they said, we have to make this real, and they created the National Research Council. And as a matter of fact, Millikan, as in the Millikan oil drop experiment, ran the Physical Sciences and Engineering Division within the Academy as a volunteer, and it was the one that was active and actually put the program together in 1916. He was actually became a reservist, a major in the U.S. Army with the approaching, in the Signal Corps with the approaching of World War I. And then as we got into the interwar years and towards World War II, things really began to pick up. Now here's where it begins to touch the area of nonproliferation. There were 3 studies done in 1941 about the possibility of whether or not you could build a nuclear weapon, an atomic bomb. They formed a group that was called the Uranium Committee. Just to make sure I don't miss any of the key names here, I'm not going to read you the whole list. But it was chaired by Arthur Compton. So if you know a bit about nuclear physics history, you should recognize Arthur Compton's name. Ernest Lawrence, that ought to be another name you recognize. John Slater, Slater orbitals, you got that in chemistry somewhere, was on the committee. And finally, there were several others, but one other I'll mention that you probably have not heard of was an individual named Oliver Buckley. He was the president of Bell Laboratories. And I won't say more about Oliver Buckley now, but he's going to return in this story of proliferation in the academies when we get to a few more slides. Well, if you go back and read these, there were actually a series of 3 reports that were written. 2 interim reports that were written more or less as letters, and then the final report. And by the way, you can look at any National Academy report, I think, that's about ever been done on the web. You can pull them up, at least the more recent ones. But you go back into 1941, you can see it's got a handwritten cover. The report's dated November 6, 1941. It was originally classified. That's since been crossed out, but it used to say classified, here and here, secret. Handwritten. When you look inside, the report's typed, but all the equations are written in by hand. So it's a rather interesting. The graphs are all drawn by hand. It's rather interesting to read. But when you read through it, they actually said there's about 3 things that we can imagine you would use in a war effort with fission. One is you could build explosives of tremendous power. We'll return to that story a bit later on. You can also use it for propulsion in ships, submarines as well as surface ships. And as we all know, nuclear submarines, nuclear navy, etc., that eventually came true. And thirdly, you could build radiological weapons. Well, it didn't take long for them to quickly dismiss that when it wasn't in our culture to build radiological weapons, and scatter nuclear isotopes around the landscape and go about it. Well, the one that they began to pursue most fervently, and this is where Eugene Wigner played a big role, was pursuing nuclear explosives. And as a matter of fact, if you read the concluding recommendation that came out of that report, what it concluded in November 6, 1941, is that a fission bomb of superlatively destructive power will result from bringing together a sufficient mass of element U-235. In fact, the report talks about element U-235. It also talks about element 94, because element 94, plutonium, didn't have a name as of the time. So the report only refers to it as element 94, which had actually not yet been created. Well, the second thing that the report went to after that was nuclear propulsion. This happens to be the USS George Washington, which was the first Polaris submarine. It was the second nuclear submarine, the Nautilus, as a technology demonstrator, sailed first. But this is the submarine. And in fact, if you read what the report concluded about this was a letter report. It was written on 17 May 1941, so it preceded the other report by about 6 months. And it concluded that a fission reactor could be used as a power source on submarines and other ships, but can hardly have an important application within less than 3 years from the time of production of the first chain reaction. So the first reaction in Chicago happened in 1942. That means they thought that it would be impossible to actually build a nuclear-powered submarine or nuclear propulsion system for a ship prior to about 1945. And of course, the Nautilus first sailed in 1954. So it actually took about 12 years from the first fission reaction until it was actually placed aboard a ship. But they had the foresight to be able to tell that this would happen. Now, one of the interesting things also about the report, if you read it, they actually go through that report and they look at trying to calculate the amount of material you need for critical mass. And it was an interesting calculation that they did. I won't comment on its accuracy, but nevertheless, it was an analysis that they did. Well, what happened after that? Well, the war concluded. And the next thing that happened was, let's talk about ballistic missiles. Well, at the end of the war, there was something called Operation Paperclip. What Operation Paperclip did is it brought a variety of German scientists and engineers to the United States, those involved with rocketry, radar, nuclear energy, a whole variety. I mean, as a matter of fact, it's very interesting that actually he was an advisor to me because he had long since retired. But when I first got to Sandy in 1979, the person who was a senior manager in charge of the radar group there was a guy named Ottmar Stutzer. And he actually had been in the Luftwaffe during World War II and came over as Operation Paperclip and ran the radar program at Sandy at the time and later became an advisor to me. He worked well into his 90s and was a very, very bright individual. But I think one of the things that is most famous for were Werner von Braun and the other engineers and scientists that came from Peenemünde and went to White Sands. And what you see on the right or on your left is a V-2 rocket. And on the right, you see a V-2 that has a WAC Corporal on the top, which was our first experiments in trying to stage rockets, something that von Braun actually had wanted to do for quite some time. The reason these were here is that there was a study done in 1946 by the Academies on the feasibility of using long-range rockets, as an offensive weapon. Not pointed directly towards nuclear weapons, but just in general. It was a study that was done at the restricted level, which today would be something we would call unclassified controlled information. So it's not secret, but yet it's above OUO. It's something you just control it within the community that actually needs to see it. And what I do know is if I look at this committee, a number of interesting people were on this committee. For example, Hugh Dryden was on the committee. So if you ever heard of the Dryden Test Center at Edwards Air Force Base, that was the Dryden. It also included Millikan. Millikan has resurfaced, who was there when the first National Research Council was created, the Millikan oil drop experiment and all that we all know about. Also, a fellow by the name of Zworykin, who at RCA is deemed as being the inventor of the TV, was on this committee. And lo and behold, Oliver Buckley was on this committee as well, who was on the original uranium committee. And what's interesting, the report written at this level makes no comment about the possibility of putting nuclear weapons on top of rockets. But you will never convince me that maybe it was never said, never written down, but you will not convince me that at least Buckley had the notion that if warheads could be built small enough, they could be placed on top of ballistic rockets. So you could argue that the first inkling notion of these pieces coming together for an ICBM program happened in 1946 in the Academies study, and I would embed that within the thoughts of Oliver Buckley at the very least to do that. Oliver Buckley was still the president of AT&T Bell Laboratories. Also another bit of history across the DOE complex. During World War II, what you now know as Sandia was the Z division of Los Alamos. It was the ordnance laboratory at Los Alamos. And spent a lot of, they actually had gotten moved up to Wendover Field during the equipping of the aircraft to make B-29s accommodate both Fat Man and Little Boy. Towards the end of the war, about September of 1945 or August, I think the first group showed up. They moved down to Kirtland Air Force Base in Albuquerque, which is now, for those of you who have ever been there, flying into the Albuquerque International Airport. The Z Division moved there. And in 1947, which is coincident with the creation of the Atomic Energy Commission and a lot of other things that sort of set on course modern motion, in 1947, what was then the Atomic Energy Commission decided that they wanted to have what was called a standing stockpile of wooden bombs. In other words, they wanted it to be just like any other bomb. Put it on a shelf, and if a war comes, you take it off. Not a gadget that took an engineer to fly on board the plane and arm it on the way to the target, like it happened during World War II. And when that happened, that they made the transition to wanting to actually manufacture atomic bombs. University of California, that had been running Los Alamos, said, wait a minute, that's not what we do. And so the notion had been cooking inside of an advisory group to the AEC, of which Oliver Buckley was on, that it should be moved to a manufacturer of high reliability, high technology systems, electronics. And so they split Z Division off, called it Sandia Corporation, and asked AT&T Bell Laboratories Western Electric to run it. A key motivating force behind that was none other than Oliver Buckley, who returned again. So he actually touched the history of your lives 3 times. Without that fission report in 1941, I would submit that none of you would be sitting here right now. And then secondarily, the notion of mating it to a rocket in 1946. And then between 47 and ultimately in 49, the creation of a second laboratory inside of the DOE complex, the weapons complex on the weapons side directly at Sandia. So interesting history of how all those pieces together. Well, one of the things that also became obvious after that was, what about putting it onto a submarine? Well, there was a study done in 1956. As a matter of fact, Kelly Johnson, who founded the Lockheed Skunk Works, was on this particular committee, wanted to look at the feasibility of putting a nuclear weapon on the tip of a ballistic missile that could be fired from a submarine. And in essence, beginning what was going to become the third leg of the triad of the strategic deterrent. So this is a picture of a Polaris A3 missile that could be fired out of a ship like the USS George Washington. And a study in 1956 that was classified at the time, in fact I didn't check, it might still be classified, talked about the feasibility of putting warheads onto missiles, and that gave birth to the submarine program. And actually, for my Lockheed history in my life, that report led to the creation of the Lockheed facility that now sits in Sunnyvale, California. So if you've ever worked the satellite or ballistic missile programs that Lockheed has and you went to Sunnyvale, it was born out of this National Academy study that was done in 1956. Well, after that, what else could you do with space? Well, pretty soon, if you think about it, what about figuring out what the other guys were doing? So this is now the very beginning of what we would call modern nonproliferation. You got to know what the other guys doing. So at the end of World War II, we, as in the U.S., tried to fly things like B-29s over Russia. That didn't work real well. They got shot down. Then they modified a B-57, which was a jet, extra big wings, got to about 50,000 feet. That didn't work. So that's when they asked Kelly Johnson to build the U-2, which flies at 70,000 feet. And it overflew the Soviet Union from 1956 until 1960, before Francis Gary Powers was shot down. But the whole idea was to monitor what people thought was first a bomber gap and then a missile gap with the Soviet Union, trying to surveil what the other side was doing. Well, people realized quickly then, but what about the possibility? Okay, we've been doing this airplane stuff. Is it possible that we could potentially do this from space? Along came another National Academy study trying to evaluate the possibility of doing surveillance from space. Well, back then, that was long before the days of digital imaging and the sort of things that we do today. So, okay, I take a picture from a satellite, which we know how to build satellites by We knew that satellites were possible. By the time we'd flown it, in fact, this is actually a picture of Explorer 1 being launched in January of 1958. So we knew that satellites could happen. Wernher von Braun eventually became a member of the Academy of Engineering in 1966. He was in the 3rd class. But we knew that we could build satellites. But what about doing something? And we knew we could figure out, could we put a camera on one? So the work was done to build a higher resolution camera, recommended by an Academy study, build a camera that can actually image from an orbit and see what the people are doing on the ground. Well, now the problem is there's nothing digital. How are you going to get the signal back down to the ground? So they came up and created a program called Corona, where they actually took it on film, and then they kicked out a canister, and the canister re-entered over the Pacific, and they'd go out with an airplane with a hook behind it, and they'd snag the parachute as the canister went by, and they'd retrieve the film. Came out of a National Academy study. It was called Project Corona, and that's actually how it was done. And believe it or not, I've seen film clips of it. They took a C-130 with a hook, and they grabbed the parachute out of the air and reeled in the film. Right? And so that was the birth of surveillance from space. Right? And obviously now it's evolved, and we're going to come back to the space surveillance story again later. But that is basically how the whole thing began. Well, by this time, there was a political pressure beginning to build on the notion of notion of proliferation became really common. We had the bomb. The Russians set off Joe a couple years after us. They were shortly behind us on a thermonuclear weapon. They actually set off a layer cake design before we did, so the Russians were clearly moving very quickly. There was concern they might even be ahead of us at the time, and there was concern about, I remember as a little kid, people talking about, cesium that was getting into the grass, into the cows, into the milk, and then little kids were drinking it. Maybe that's why my hair fell out, I don't know. But there was a real concern about this, and so they began negotiating treaties that limited the size of a detonation, eventually moved detonations underground. And this is actually President Kennedy signing the test ban treaty that in 1963 moved all testing underground. So there were a whole series of things that happened. We signed, in 1963, the underground testing treaty was signed. That's this one that was signed by the U.S., the USSR, and Great Britain, and then eventually France. And obviously by the time the British set off their first nuclear weapon in, I think, 1952. So by the time we got to the early 1950s, there were 3 nuclear powers. France, I think, was about 1960. China was about 1964 or 5. I didn't look up the years exactly, but you can see sort of this pace of things were proliferating. And the notion was to have everyone begin to abide by these treaties. But the question, okay, what do you put in a treaty? How do you limit the size? Where do you put it? How are you going to make sure that you do the right things to share with the other side what you might be trying to do in your test? So there was a series of Academy studies that were done that advised the government on what you actually should allow and how you should measure and detect and monitor, so forth, how these actual tests were happening in each other's countries. So that started in 1963, and there were just a series of studies that were done, in fact, as recently as 2012, that really deal now with things like treaty ratification and trying to understand whether or not somebody's cheating, how you monitor things, and so forth. But still a very active area of study. Well, so far we're in 1963. All that exists is the National Academy of Sciences and the National Research Council. And all of a sudden, your own Eugene Wigner returns to the scene. He was actually elected into the Academy in 1945. He had become a U.S. citizen in 1937. But most importantly, at least in the National Academy of Engineering story, one of his students was Frederick Seitz. Now, old Fred Seitz is actually almost more of a theoretical material scientist than he is you think of him as being a physicist. Everybody knows things like the Wigner-Seitz cells and those sort of things. But anyway, old Fred, he became the president of the National Academy of Sciences. And it's interesting, when the Academy was formed in 1863, it was people who were engineers, physicians, and scientists that came from industry, academia, and government. By the time we got to the end of World War I, it became almost all more pure scientists and almost all academic. And the government said, wait a minute, we created you in the first place because we wanted this balanced perspective of how we handle these things. And we want an industrial perspective. We want to know if this stuff is real. And so there was pressure building. In fact, if you looked at a lot of the studies that were done and the people who did them, I'd argue that deciding that you could put a warhead on top of a rocket, or that you could put a warhead on top of a ballistic missile out of a submarine, or that you could actually toss canisters of film out from orbit and catch it, are as much engineering as they are science, and probably quite a bit more so. And so the government recognized that and said, most of the things we're asking you to do are more engineering. And so there was pressure built to even create a completely separate Academy of Engineering. And Seitz, who was the president of the NAS at the time, said, I'm not going to do that, because if I look at the original charter that Lincoln signed, what it said is I can govern myself any way that I want and I can elect my own members. So Seitz and the NAS Council, basically their board of directors, took it upon themselves to create a second academy under the same construct as the NAS. And so now there's sort of a capital NAS that's the umbrella over all, and there's now three pieces inside. There's NAS, there's NAE, and there's the NRC. Right? So we have these bodies. The NRC really serves the three other academies, because later there was an Academy of Medicine created too. Happened by a path that took a couple of decades, the details of which are not important. But today there are actually three academies: Sciences, Engineering, and Medicine. The way it's branded is the National Academies of Sciences, Engineering, and Medicine. So about once a week, if you pick up a newspaper, you'll see reference to some study done by the National Academies of Sciences, Engineering, and Medicine. There was one done just a few weeks ago about GMOs, genetically modified foods, et cetera. And there was another one I just saw referenced something related to cyber. So these things come out periodically. You'll see that's how they're branded when they actually come out. But it all happened because Seitz, who was Wigner's student, was the one who decided to create this separate standing engineering academy underneath. And in fact, the goal of the engineering academy is to have half of its membership from business, from industry. About 40% from academia and about 10% from government, which includes things like national laboratories that were actually true government employees. Quite frankly, it's drifted a bit from then. It's now closer to a little bit less than 40% that's business. We're trying to get that moved around a bit, but there's still a very, very strong business voice. As a matter of fact, it's interesting that when I look at some of the previous lectures that you've had here, Craig Barrett, in fact, Craig Barrett was the chairman of the board of the National Academy of Engineering a few years back. Our current chairman of the board for another 5 days is Chad Holliday, who I think is your next Wigner speech in maybe August or September, sometime in the fall. So you'll see Chad. He's a retired CEO of DuPont, and he's currently the non-executive chairman of Shell Oil. Anyway, so here's that first class of the National Academy, 25 members, and 50% from industry, 40% from government. Actually, it was 52% from industry, 40% from academia, and 8% from government. You can't quite take 25 and chop it evenly into 50, 40, 10 unless you move an arm from somebody over to the other category. So that was the original body, and typically by that you can see they're all very senior. One thing that's interesting about the academy is that the average age of election is about 62. The average age of a member is about 73. Sort of interesting, but if you think about it, people get elected to membership typically based on a lifetime of achievement. There occasionally, I think, Bill Gates was, I think, 42 when he was elected. Steve Wozniak, I think, was around 50. So 50 is really, some people do get elected to 50. That's rather on the young side to do that, but it's based on a career worth of accomplishments. That's why when we actually do these studies, it turns out about a third of the members are typically academy members. The other 2/3 are people that are subject matter experts of relevance and oftentimes younger, to sort of get the young mix in, and those many people eventually are elected into membership and so forth. But very, very senior people that were, and in fact still are. If you look at the demographics, that age of election between low 60s, high 50s has been true ever since 1964. And it's based on the fact that it takes a lifetime of accomplishment to be recognized. If you come up with some innovation in the laboratory when you're 32 years old, by the time it finally has a real impact somewhere, it's going to probably take 20 years. So you think about it, there's very, very few things at the roots of which don't. People think about, well, look at how quickly we got the iPhone. Well, not really. As you go back and look at the work on strained layer superlattices and compound semiconductors that make those things possible, that work goes back to the 1980s. So the journey of the physics through to the iPhone, was at least 20 years and not 20 months. Anyway. So what about some of the other things? We got rolling into the Cold War right now, and we created something that was called The Committee on International Security and Arms Control, or CISAC, it was established in 1980. It still exists to this day, and many of the studies that are done involving nonproliferation are done through that particular activity. And it's meant to bring experts to, once again, science, technology, medicine, from industry and government into this whole issue of weapons proliferation and international security. That picture above happens to be an attack submarine named the Growler, and it's a Regulus missile on the top, which is an early version of a cruise missile. But the notion when you start talking about proliferation, there's all kinds of ways to proliferate. There's bombs, there's missiles that come from submarines, that come from land, there's cruise missiles, etc., a whole variety of these other things, but these all have been there. Next, if you think about, we get into the 1980s, right, and there were a whole series of studies that were done at that time by CISAC that addressed the whole number of general issues around nonproliferation and disarmament. In fact, there was a study done in 1985 on nuclear arms control, its background and its issues, that looked at the whole, tried to do a broad scoping study of where we stood with nuclear arms control. Shortly thereafter, there was another study that was requested that was called, it was a seminar series on crisis management in the nuclear age. That was 1986. And shortly thereafter, this was all information that was being fed back into the administration, because shortly thereafter, there was a summit between Reagan and Gorbachev, and that eventually led to the Intermediate Range Nuclear Weapons Treaty. At that point, they came back to CISAC and they issued another report in 1988 on Reykjavik and beyond, and that looked at what were the potential advantages, disadvantaged outcomes, of deep reductions in strategic nuclear arsenals and the future direction of arms control. Well, as we get on that time, we see that, of course, our major adversary, even in the 1980s, was still the Soviet Union. This is a picture of an F-102 interceptor of the U.S. trailing a Soviet Bear bomber, which is one of their heavy nuclear bombers, along with the backfire. This was actually a study done looking at capabilities of both sides. It was a joint study done between the U.S. Academy and the Russian Academy, the Soviet Academy. That study was done in 1991. It was one product of this relationship between the two academies. It's very interesting that some of the changes that are happening in Russia nowadays are changing the independence of the Russian Academy, and how that will interfere with their ability to collaborate with other academies around the globe is sort of going to be interesting to see how that unfolds. But there's been a lot of interaction between the academies over the course of the last couple of decades, at least through the 90s and into the early 2000s, looking at a variety of workshop and other things around nuclear security, environments, and so forth. In fact, the last one that was done was a workshop that was done in 2009, and the idea of that workshop was to project what the world would look like by the time we got to 2015. I should go back and look and see how accurate their prediction was. I didn't do that, however. One of the things that came out of these studies was this notion of how do you actually ensure when somebody says they're going to take it out of service, it's really out of service. Well, out of an Academy study that was done in 1997, the notion was chop things apart, that they can't be put back together again. So this was a recommendation that came out of a study. There were a couple of studies done in 97 and 2001 on arms reduction, and then another one on monitoring of nuclear weapons and their nuclear explosive materials that was done in 2005. A little bit closer to home here, there have been a variety of studies that have been done on the DOE and on the NNSA, on the DOE complex and on the weapons complex. In 1989, in fact, I remember this one being done, there was a study done that looked at the management of the nuclear weapons complex. In 2011, in fact, as I went back and counted, I think there's been about 8 studies that have been done in some way or another on the NNSA complex, on the DOE complex, on research in the DOE, research at the weapons laboratories, et cetera, and how all these pieces come together. As a matter of fact, there are 2 right now for the NNSA that are actually ongoing, again, looking at the whole issue of how you manage these laboratories and manage the complex, how you make sure that it's a vibrant, healthy society, an environment for doing research and development, et cetera. And it's been very interesting to see recommendations come by, and quite frankly, you often wonder how well the administrations will listen to these various bits of advice. Some things are implemented, some things seem not to be. But clearly there's a lot of interest on the part of the DOE and on the part of the Congress to try to really get this thing right. And their independent source to turn to for that has always been the National Academy to do that. As I said, there are 2 ongoing right now. Well, there have been other studies that have happened since that time that happened even outside of CISAC. There's another group that within the National Academies called the Policy and Government Affairs Division. It's in what would be within the NRC, the working arm, or called PGA. And within there's actually a committee that's called Strengthening the U.S.-Russian Cooperation on Nuclear Nonproliferation. And that led to a 2005 report that identified ways that the two countries could cooperate better in the whole notion of nonproliferation and arms control. And it turned out that the main recommendation was really more cultural than anything else. And it was a recommendation to reinvigorate the relationship between the two governments as a true partnership in nonproliferation. Well, in addition to work on nonproliferation, there's also things that sometimes people would call counterproliferation. And there's what are the things that you do that if pure negotiation you can't negotiate, what do you do to make sure you know that the other side is actually being honest in what they bring to these discussions, that someone's not trying to cheat, or that somebody who's not even a party to the discussions in the first place isn't doing something outside of some larger generic framework, perhaps sponsored through the United Nations. So there are other things that are done related to strategic arms. We did one in 2009 that looked at assessing and certifying the reliability of the U.S. nuclear weapons stockpile. I'm sure some of you here have heard of a term, scientific-based stockpile stewardship, about using above-ground simulations and computation to try to understand the reliability and the safety of our nuclear arsenal. And this was an external assessment of how well that process was going. We did another one in 2012 looking at whether or not you could do boost phase intercept of enemy intercontinental missiles by intercepting them in the boost phase off of a Navy ship. So, for example, if you're worried about a North Korea, for example, that might launch a weapon, if you park that naval asset well into international waters off of the coast of a potential adversary and they fired a missile, it's easier to get it, the thought went, in the boost phase before it's moving very fast and it's very far away, that the intercept ought to be an easier thing to do. So there was a study done to evaluate that as a possibility. There were other studies done that were looking at short, medium, intermittent range ballistic missiles threats from rogue states that could be deployed against either our forces or our allies overseas. Well, also in this whole realm is the notion of deterrence. There's a picture of a cruise missile flying over that looks like the Nevada test site. Where the nation has come and asked for the academies for advice on what you can do to and evaluate deterrence and what it actually means. So there was a study done in 2014 that looked at what were the effective analytical tools that were needed to determine what makes nuclear deterrent effective and in the current reliability and in the current political realities of the 21st century. Well, we continue to worry about surveillance, right? This goes well beyond the days of Corona. But there were, I won't read the titles for you, but there were studies done. There was a study done in 92, 93, one in 99, one in 2005, one in 2010, two in 2013, and one in 2015, another in 2016, that actually look at, in some way or another, of how space surveillance might impact your ability to monitor what adversaries are doing, either to break treaties or people who are not signatories to treaties might be doing. And unfortunately, I can't say very much about the ones that were just recently. I reviewed them, in fact, recently, but both of those studies are classified at SITK, and so there's not things that we can be shared publicly. But there is still continued interest on the effectiveness of a variety of these surveillance techniques. Well, there's other things to worry about besides just the former Soviet Union or even China. If you start thinking about other powers that have joined the nuclear club, or India, for example, and Pakistan, there are a number of CISAC-sponsored dialogues. So, for example, there's an India dialogue that was started in 2001. In 2013, there was an India-U.S. cooperation on global security workshop around nuclear materials that was done. There was a study done in 2015 that was a joint study between Brazil and the U.S. And then there was a study looking internationally at how you can control nuclear materials that was done in 2005. So it really covered the gambit. Once again, a little bit closer back to home, as I mentioned the NNSA before, in addition to looking at issues around governance of the DOE and the NNSA, there's also been a number of studies that have been done that have looked at the facilities requirements for that. So if I look here between 2004 and 2015, so that's a total of about 10 years, There are a total of 6 studies that were done just on the NNSA, its facilities, its security, the quality of its science, and its management. And there are 2 more that are ongoing right now. So that gives you 14, since that gives you a total of 6, that gives you a total of 8 that have happened in the last 14 years. Almost one a year of being done and being revisited. It's still a very active area. Also, other things have been done, for example, in managing excess nuclear materials and spent nuclear fuel, which touches back into the power realm. Well, things got even more exciting after 2011. Been a whole variety of studies that have been done that have looked at things like rogue states, non-state actors that might in fact go back and return to the number 3 item on the fission letter of 1941 involving radiological weapons. Right? What do you do to control them? What do you do to detect them? So there have been varieties of studies that have been done in that realm. There have been other studies done in the area of nuclear detection. So I think many of you know things like NUDET, the nuclear detection payloads. They all started with the satellite that was built by Los Alamos and Sandy in 1963 called Vela. Right? And to this very day, these NUDET, nuclear detonation detectors, fly on GPS and DSP, which are defense payloads, that are meant to monitor. They look for visible light and infrared light signatures that will tell you what's been set off and et cetera, how it might work. Things like SIBRs are directed at that. So there's still a variety of nuclear payloads. In fact, this whole notion of detecting clandestine or unaccounted for nuclear tests is another piece of those 2 space studies that I just referred to. So still a very, very active story. One little sidelight story of history here that I'll tell you that I always thought was cute. I actually worked on the successors to the Vela satellites that flew at Sandy. At one point, those reported into me. But that actually detectors that are on those satellites, they're called bang meters. Now, if you heard me say a bang meter detects nuclear detections, you think, well, nuclear explosions make a bang. That would kind of make sense, except that it's spelled with an H, B-H-A-N-G. So maybe you can correct me if I'm wrong here, Tom, but the story goes, I think that's the Hindu word for smoke. And so the idea was when the guys at Los Alamos and Sandia said they could build a detector that could, from orbit, could detect a nuclear detonation, the Air Force said, what are you guys smoking? And that's where the name bang meter came from. Nothing to do with the nuclear explosion, but rather you guys must be smoking something if you think you can detect a nuclear detonation from space. But lo and behold, guess what? They could, and we still can, and we still do. At least look for it. What about in the future? Well, we have another study ongoing right now on high-speed weapons, like hypersonics. The interesting thing about hypersonics, so if you have a bad guy, all of a sudden somebody decides they're going to point a missile with a nuclear warhead on it and launch it at the U.S., and you see them set it up, but you don't have any F-16s from the Air Force or F-18s from the Navy nearby. What are you going to do? We only have one rapid response weapon right now in the arsenal, and it's our own nuclear missiles. And we're not going to lob a nuclear warhead at some third world country because we see them propping up a missile. So what can you do? So starting actually back in the mid-2000s, the notion came of putting precisely guided but conventional warheads, for example, on a Trident, so you could take out in only a few minutes another target. Well, another option is to build vehicles like this one. This is actually one that we built at the Skunk Works called HTV-2. Flies at Mach 20. But the idea would be that you could launch this, say, in the United States. You could reach any place in the globe within 30 minutes. And, you know, of course, when it re-enters the atmosphere, it slows down to maybe about Mach 6. But even at Mach 6, there's a whole lot of E and V squared at Mach 6. So if it hits you, it doesn't need to be nuclear to take out your target. So now this whole issue becomes you've now got strategic weapons that are, in fact, not nuclear. And how do these things get addressed in treaties? So at this point, these are just really experiments. There's no intent to field anything like this, but just to explore the technological feasibility of it. But there's no doubt that if these things become real, it's going to. I would be surprised if it doesn't require some kind of renegotiation. So that's being done. Now, what about tomorrow? Well, just a few closing comments about the Academy here. We created something called the Grand Challenges for Engineering. So what are the Grand Challenges for Engineering? I'm going to go back and forth here between slides here in a second. Here are the Grand Challenges of Engineering. There were 14 of them. Now, where did they come from? Well, it turns out that in about 2002 or so, the notion was, what were the greatest engineering achievements of the 20th century? And there was a group to pull together, and they came up with a list of the 20 greatest engineering achievements in the 20th century. And in fact, if I asked you all to take out of a piece of paper and write down, I bet you get at least 10 of them right. Number one on the list actually is electrification, right? Interstate highways on the list, nuclear energy is on the list, airplane, automobile, computing, telecommunications are on the list. And they're all relatively obvious. So then the next question is, well, what are going to be the 20 greatest inventions of the 21st century? How do you answer that question? So that got morphed into what are the greatest challenges that need to be solved? And there was a committee pulled together. It was chaired by Bill Perry, former Secretary of Defense. Steve Jobs was on it. Bill Gates. No, actually, Jobs was not. Bill Gates was on it. Ray Kurzweil was on it. Craig Vintner was on it. Very, very people known to be very, very insightful in their ability to assess where technology was going. Excuse me. And they came up with this list of 14. What's interesting, you'll see one of them up there is prevent nuclear terror. So it's still this issue of what are you going to do about nonproliferation and counterproliferation. So we did this. It was a nice study. You can go to if you go to the web and you Google grand challenges of engineering, it'll take you right to this list, and there's a whole variety. You can learn more about it than you'd ever possibly even want to know. What was interesting about it, that's in fact what the hardcover looks like, but what's interesting about it is there were 3 individuals in the academic world, Rick Miller, who is now the president of Olin College up in New England, Tom Casaleas, who was the dean of engineering at Duke, who's now the provost at Virginia, and Yanis Yorsis, who is the dean of engineering at USC, got together and said, let's take these grand challenges to create a scholars program with it. 120, as of last spring of 2015, 123 deans had signed up committing themselves to producing what a Grand Challenge Scholars are. And the Grand Challenge Scholars, I'll come and say, do I have a chart in here? No, so I'll just articulate this. Grand Challenge Scholars go through a normal program at the university, typically in engineering. It doesn't really necessarily have to be. But then there's some requirements that go beyond just being your normal engineering student. You need to commit to doing something multidisciplinary. And that doesn't mean the physicist working with the double E anymore. It means an engineer and a computational person working with somebody in life sciences or whatever. It means an international experience, which, by the way, doesn't mean going and working at the Honda or the Volkswagen plant here somewhere in Tennessee, right, or Ohio. What it means is going and having an experience. It doesn't mean going to Canada either. But what it means is going and getting involved. Perhaps you're going to go and work on a water system that's going to be installed in somewhere in the developing world. So multidisciplinary, multicultural, right? Also has to have some entrepreneurship in it. So you know what it's like to actually make things real. There's a total of 5 criteria. I won't recite them all. Those are 3 that are perhaps the most relevant. And their goal to the president, as in Obama, was to produce 20,000 of these Grand Challenge engineers by the time we got to the year 2020. Well, so far, there have been 29, my list might be out of date because they just went up to 29 schools. And hopefully there's all something up there you all recognize, right? Tennessee was one of the schools that has a program like this in place. And in fact, I do know for a fact that there are students who have picked preventing nuclear terror as, in fact, the focus of what they want to do for their study. So it might be to try to get an assignment at in another country where we have, so for example, at Sandia, we had this thing called the Cooperative Monitoring Center that was in Jordan, that was looking at controlling proliferation in the Middle East. Get an assignment there and live in Jordan for 3 months and see what it's like. That's the whole idea behind how this thing works. So this is meant to generate that next realm of students. And the thing that we find most interesting about this, I don't want to dwell on this, one of the concerns that we have in engineering and physical sciences is that it is sorely underrepresented with women and with underrepresented minorities. 18% of the undergraduates today in engineering are women, but yet women are more than half the population. 13% of the population is African American, but 4% are in engineering. I think 18% of the population is Hispanic, and it's like 6%, right? However, if you look at the students that have signed up for this Grand Challenge program, it matches the national demographics. 54% of the students that are in this are women. 13% of the students that are in this are African American, and 18% of the students that are in this are Hispanic. So it matches the national demographics. So it seems to have very, very broad appeal. Maybe it would take a psychologist to answer why that is true. It's because maybe people are getting to solve problems. Engineering is really about solving problems, not building gizmos, right? You build the gizmo to solve a problem, right? But it seems to be attracting, and we need it. I mean, we are in a talent race. You talk to the Chinese and they claim that they're short of talent, right? Everybody in the world wants talent, right? Including here in the US. And this is a way, we think, to attract a much broader sort of feeder base into the engineering and physical sciences pool that the country really needs to remain competitive. So, that's the Academies, a little bit of self ideas thrown in on top of where nonproliferation has been and will go here at the National Academies and in the US.
So, Al, thank you very much for a really interesting talk. And you've touched on a number of things, but since you ended with sort of Grand Challenge scholars, and I see a lot of, summer is the time when we get a lot of students on campus, but also we have both with the University of Tennessee, a Bredesen program that brings about 120 or so graduate students here, but also through other universities. We have about a cohort of 150 PhD students here. So, and it seems to me that they're really interested in sort of this broad-based experience that academia offers, but also the national labs. Now, given your broad-based experience, first at the national lab, and then at the Lockheed Martin Skunk Works, and not the National Academy, what advice would you have for them as they think about another 30 or 40-year exciting career?
Well, let me ask a question first, and I should have done this. Are there any Grand Challenge scholars sitting here in the audience that are at UNCSO? We've got one. Are you enjoying it? Very good. Okay, it's interesting. Everyone says the world is so much different than it was before, and I'm not sure that's ever really true. I mean, I think there's a lot more constancy in how society evolves, and people sometimes give it credit. And I think, of course, the most important thing is to get a very, very sound, competent skill in whatever your profession is. And I think one example to look at that is people, I want to be a systems engineer. So they want to go off and find some course they can take, or 4 courses, they make themselves into a system engineer. But I can tell you that in the real world, when you build real systems, you don't become a systems engineer by going off and taking a few courses. You get there by doing it, by working on teams. So, if you want to lead a high technology team, as a chief engineer, as a program manager, et cetera, as a systems engineer, you do it by being extremely good at whatever your own discipline is. If you're an electrical engineer, digital circuit designer, materials, whatever it might be, make sure you are extremely competent at what you do. But then secondarily, make sure you can really, really work on a team, right? Really work on a team. Learn to listen to other people. Right, don't worry about who gets credit, right? It's amazing what you can do without worrying about who's going to get credit for it. The team will get credit. Credit does not come in a unit whole. If the team succeeds, everybody gets credit for it, right? And so learning how to really work as a team and exploit the differences, and different perspectives amongst your team are really important. And this notion of diversity on a team, and I mean diversity in all kinds of dimensions. I don't mean just gender. I don't just mean ethnicity. All kinds. So let me ask you a rhetorical question in that regard. If I gave you a choice of 2 teams, right? One team, I'll even pick the local school. One team are all mechanical engineers from UT. And I don't mean Texas, right? Team 2, mechanicals, electricals, materials, physics, chemical engineer. And they come from schools all across the country. Which team do you think is going to give you the most creative solution? It's going to be the second team, right? And what's wonderful about a national laboratory, in a program that you're in here, you don't all go to the University of Tennessee. You're not all the same major. You're mixed in with other people. So learn from one another and learn to work together. And now I might show a bit of my age with all this, that, humans evolve to interact with one another, and I think that means more than just by tweeting each other. And the reason that I say that, there have been lots of psychological studies that are being done that your communications are a lot more than words. So right now, I mean, we're having a dialogue, but we are at least subconsciously picking up signals from each other that are a lot more than verbal. Facial expressions, nods, etc., the way the eyes respond. Communications are really, really important. So I think extreme competence in your own field. I think recognizing that people work best as teams and they working together to do that. Strong communication skills. One of my favorite questions to ask undergraduates is, how many of you are going to have a career in sales? And usually like one hand goes up in a class of, say, 50. Well, in fact, it's everybody, right? You got to sell your ideas and yourself to your teammates and to your superiors, et cetera, right? So strong communication skills. By the way, a lot of engineers are not very good at that, especially written. You know, I've seen far too many engineers with PhDs who can't write a coherent sentence. So being able to be a strong communicator is another good one. And then I think the final piece is have a broad worldly perspective. You know, if you are, you know, whatever your area of specialization is, don't just simply read the expert journal in that little narrow slice of your own field, right? If you're a double E, don't read just the narrow slice of whatever your area of specialization. At least read IEEE Spectrum when it comes out. But even beyond that, pick up a newspaper. Pick up a magazine like Foreign Affairs. Pick up the Atlantic Monthly. You know, read. But don't stay a broad area. In fact, one of the fun things that's really interesting to do is there are a lot of news clipping services out there. Some event happens. Pull out the story the way it was written by the Los Angeles Times, about as far left as you can get, and one written by, say, the Wall Street Journal, which is not extreme far right, but certainly right of center, or maybe the Washington Post a little bit more in the middle. And so you read those, and same story, but quite different spins. So those are just some very general things that I think are really going to be critical for you to do as you let your career progress.
Well, last night at dinner we had a little bit of a conversation about National Academy, and since as executive officer you're here, we want to pick your brain on that. And one of the things that the laboratory has been focused on, particularly of late, is this whole notion of science culture, primarily because we have, again, a lot of early career staff. As I mentioned to you, about 67% of our scientific staff have been here less than 10 years. Sort of setting expectations for their career is important. And while the lab has a lot of influence on its own, the influence through membership in the National Academy has a certain broader appeal. And so we had some conversation about what can we as an institution do to help prepare our early career scientists and not so early career scientists given the demographics of membership. Could you sort of comment on what the lab, Oak Ridge, and probably broadly the labs can do?
Well, I think first off, you know, as I made the comment, we do about 200 or 250 studies and workshops a year. The Academy's enterprise is not small. It's about $300 million a year of activity, so it's not as big as an Oak Ridge, but it's certainly not a small thing. And 2/3 of the work is done by people who are not Academy members, but by people that tend to be younger in expertise. So if you have the opportunity and you're asked to do one of those things, you know, you should certainly do whatever you can to be able to accept and do that. Another easy way to get involved is as in the frontiers of engineering. I know Klaus has been very active. There must be other people from Oak Ridge besides you who have been in that program, right? So when there's these series of programs called Frontiers of Engineering, which are intended for people that are about 40, 45 or younger. So they're kind of late, early, or mid-career individuals. And they come from all different disciplines, all kinds of places. There's one done each year that's US only. That's about 100 young people. And then there are a total of 5 others that are done bilaterally. One with Germany, one with the EU, one with Japan, one with China, and one with India. Right? So there are 5 so far that exist. They typically are every other year. They alternate locations. There's about 30 or 40 US people in each one of these things. But if you're invited to go to one of those, you should. You'll get your name. Somebody will turn in your name. All I would do is turn in your name and your email address and a phone number, and then you would be reached out and asked for a bio. But anyone who's an Academy member can put your name down, and there are 5. There are 5 either current or former Oak Ridge people that are Academy members, and that doesn't count some that have switched their affiliation. So if my memory's right, Jeff Wadsworth was at Oak Ridge when he was elected. But his affiliation, if you look him up in the directory now, says Patel. It doesn't say Oak Ridge. But people like Al Tribblepiece, who was your director, I think maybe right before Jeff? Or
No,
maybe
before Bill Made.
Before Bill Madia. He's retired, but he still has an affiliation listed as Oak Ridge. But any one of the members of the Academy will be asked to nominate for FOE. Anybody who's an alumni of FOE is asked to nominate names. So you've got, I know, Klaus, you probably don't have to say it now, but you might want to have that list handy, maybe give it to Tom so you know who they are. And in fact, CEOs, so Tom will be asked, for names, or Jeff is going to be asked for names. That's a great way to get started. Then people get to see you. We like to have younger people in the committees, but I maybe don't know who you are. But if we see you come through one of these Frontiers of Engineering programs and you're interactive and you leave an impression, it's very likely you're going to be asked. And in fact, activity within the Academy prior to election, it's certainly not a requirement, but it's one of the things that's looked upon very favorably before someone is actually even elected into membership. Election to membership of the Academy is, it's a very high hurdle. Each engineering academy is about the same size, but in engineering there are 2,000 members. There are about 200 foreign members, which is their only difference is where their citizenship is, so that probably not relevant here. But if you were a foreign citizen working at Oak Ridge on a green card, for example, and you were nominated, you would end up you'd go in as a foreign member, not as a U.S. member. But there's 2,000 members, and typically there are about 700 nominations a year. And you have to be nominated by another Academy member and then endorsed by 3 more Academy members. So the hurdle to even get nominated, you're not going to waste the time to write a nomination if you don't think the person is qualified. So you got 700 people with very few exceptions who are all really qualified to be in. But there's probably only 70 slots in a given year because we really stick to that 2,000. So, the old line, who died and let you in, is kind of almost true, And so of 700, only 70 are going to be picked. So it's a very, very high hurdle to get into, which is why this lifetime of accomplishment is so important. But being visible early on is important. Being active and recognized by your own peers. So for example, if you're an aerospace engineer, you darn well better be a fellow of AIAA before your nomination goes in for the Academy, or you would have virtually no chance if you're not recognized by your own peers before that happens.
Well, I've got a number of questions, but probably this is a good time to open up the questions to the audience. So,
looks like we have mics, so you might want to wait till you get the mic so it gets recorded. Here's a.
Just to try to get something going. You've talked a lot about studies that are about things that may happen in the future. And given that, particularly in the area of non-proliferation, at the moment this is a very controversial area, say, particularly with respect to North Korea and with respect to Iran. And in particular, the agreement between the United States and Iran. Do you think that the National Academy should have some role once these treaties have been agreed upon, particularly the one, say, in Iran? Because I suspect that there's a great deal of rot talked about in the public and in the political sphere. And it's good if a society can base their understanding of the value of something like that treaty if you had data or if you had a academy study of what actually happened and what the agreement is, and is the National Academy thinking that kind of thing is in fact a viable treaty? So I'm trying to get at the point about a retrospective report.
So we have done things like that in the past where an event happens, and then the question is, well, what really happened and what does it actually mean? So I'll come back to you. I'm not ducking your question. I'm going to come back to it, but I'll give you an example of how the academies can convene and how objective their viewpoints are viewed, which gets back to the thing you said too, Tom. Then I'll come back and answer this piece of it. But after the Mercando well accident happened in the Gulf 5 years ago, whatever it was, There were finger pointing going everywhere you could think of, right? Because it touched every state along the Gulf Coast, with the oil companies, the drilling companies, the Fish and Wildlife Service. Some of the oil got onto the coast of Mexico. The tourism, it was up. Everyone was pointing fingers and throwing rocks at each other. So what the Department of the Interior did is they went back and they got the National Academy and said, you figure this out. Figure out what happened, what we can do to prevent it, what do we do to clean it up. So there was a study that was done, and when the study was done, peace ensued. Everyone just said if they did it, it's going to have to be listened to. And in fact, later on, there's actually now a thing called a Gulf program that was funded out of the fine money that was paid by BP and some of the others, that actually funds a research program nationwide that's coordinated through the Academy on this whole issue of how you deal with the well. So when the Academy speaks, because of how it convenes and who it is, people listen. But what happens is somebody has to come to us and ask, right? And so I've often wondered myself why the State Department or somebody didn't come and ask the Academy to review these things. And I don't know why that hasn't happened. Occasionally, if we see a real opening, we will go and lobby for why isn't this kind of study done. But I think what happens is whenever there's a device, a situation like this one that's already so politically charged, who's going to go ask, right? Or if you take the initiative to go do that, you're very likely to anger somebody who will say, I didn't, or who will try to block it, right? So if you want to go off and do that study, I don't know whether it would be the State Department or the other side in Congress, but one of the factions would come along and say, I don't want that study done, right? And if there's no concurrence done to do it, we don't have the authority to go off and we don't have the money to just go off and do things on our own. So you've got to get, even if it's your idea, you need to have a concurrence from the government to want to go out and do one of these studies. Now, we occasionally have done studies on our own funds that are collected from overhead. I think maybe the most common one was Rising Above the Gathering Storm, in which Craig Barrett was, in fact, one of the co-chairs of that study. But that was about STEM education and the talent pipeline. That's a little bit more innocuous topic. But whenever there's been forays, to my knowledge, in areas that could be politically sensitive, unless you're asked for it. Now, it's conceivable that somebody in Congress could come along and say, just do this and make the State Department pay for it, and since they've got the purse strings, you could force that. And that's on any topic, not just this one. But the problem is that somebody's got to come along from the government, whether prompted or not, and request such a study to be done. Probably would be a very good idea for a number of things that were done. In fact, I would argue the more controversial the topic, the more useful a study like that could be. And occasionally they will come along and they're done that way, but it takes a lot of political courage on the part of someone to go off and ask for a study done in an area that can be politically charged.
Other questions? Again, if you will
Jim.
give you the mic.
So you live in a world where scientific facts matter, and where you can render an opinion that's very highly based in scientific knowledge and judgment and a GMO report or something like that. Do you think that the society as a whole in the U.S. and in the world is getting less persuaded by scientific fact? And how do you deal with that?
I don't know. That's obviously this is sort of an Al speaking. Not the Academy, and I think it almost depends what the topic is. So, and it takes time to tell. So, for example, there are some people in this room who are old enough, and including Jim and me and Tom, who remember back in the days. When you're young, you get lousy seats on the airliner, right? And you always dreaded getting a seat, what was known as the DMZ. What was the DMZ? The DMZ were those 2 rows in front of the smoking section of the airplane. Because everything from, like row 24 back was smoking, and you, son of a gun, you got in row 23. Isn't this going to be great, right? Well, all of a sudden, smoking on airplanes stopped. The reason it stopped was there was a definitive Academy study that was done on secondhand smoke. And somebody in Congress took to it and passed it, and I think the population now, except for maybe a few diehard smokers, is very delighted that it happened. But it took time to tell, right? My guess is that if you went out and you asked the population whether or not they thought that was a smart thing to do in 2015 or 16, it's a lot different than the answer you would have gotten in 1984 or whatever it was when that law was passed. A lot of what the public feels about things like GMOs, I think, is sort of emotional. Now, quite frankly, in the U.S., my sense, personally speaking, I sense there's lesser resistance to that kind of stuff in the U.S. than there is perhaps in Europe. So how it would be accepted in Europe might be culturally different than it is here. I mean, personally, quite frankly, we've been genetically modifying food by other means for the last 10,000 years. It's just that doing it with the modern tools somehow has gotten this certain pale to it. So I think it depends on the topic, and I think it depends on some time how long it actually sinks in. And I think the notion that now that scientific facts don't matter, my guess is if you went back and really looked at it at the time, that's probably always been true. That if there's sort of an emotional sense in the population about something being good or bad, that in order for a fact to convince them otherwise can take a very long time for it to sink in. And I think, unfortunately, we are not a good representative population, right? Because if you come to any of us with a series of scientific facts, you might ask lots of hard questions. But if I answer all your questions, probably by the time I'm done, you're going to agree with wherever my conclusion was. That's not true for the Jane and John Doe on the street, necessarily. They don't have the background that you have. They have a lot of emotions that are part of their, and cultural things that are part of their position that, they may respond differently.
Just to follow up on Jim's question, earlier on during your talk, you said that sometime, roughly 2 decades between sort of fundamental scientific breakthrough to iPhone or whatever. So have you sort of looked at historically what is the time that takes from a National Academies report to a substantive policy change?
It depends. There are some that happen very quickly, depending on what it is. So I'll give you one that I was personally involved in that was instantaneous. When they built the F-22 fighter, and I was at Sandy at the time, not at the Skunk Works, who designed the F-22. When I was at the Skunk Works, the Air Force was in the process of trying to deploy the F-22. And the Air Force made a mistake. There's a requirement in law that's called the live fire requirement, which means whenever you build a new weapon system, you're supposed to shoot it up and see what happens to it and try to make it more reliable. Well, obviously that would be a dumb thing to do. So if you're going to spend $11 billion to build an aircraft carrier, you're not going to blow it up to see what happens. There's got to be other ways to do that. And the same thing's true with an expensive thing like an F-22 fighter. But the Air Force forgot to ask for the waiver. And so the Air Force came to the Academy and said, we need to have you do a study to see whether or not you would recommend that we grant them a waiver in arrears. And the Air Force, we did a study. I was on the study committee that did that. And our recommendation was that, for example, including things like the right kind of above-ground peace part tests and computational modeling, you could do it and you wouldn't have to worry about it. And so our recommendation was if you did these things, you could go ahead and give them the waiver. And the Air Force got that report, and boom, instantly, it happened. The one with the secondhand smoke and airplanes took a few years. And there are others where there's a suggestion made, and unfortunately, if you look at Rising Above, how many people here have read Rising Above the Gathering Storm? Hopefully a few of you had. There was another one done 5 years later, and we're about 5 years later since. And if you read the one that was done 5 years later, it didn't really get much better. In fact, it probably got worse. And if you talk to one of the Academy members today and say, how is it today compared to 5 or 10 years ago, they'll say probably still worse. So it's one where the recommendations were never followed at all. Quite frankly, a lot of the recommendations that I've seen about DOE and NSA are not followed. Now, just because we make the recommendation doesn't mean that necessarily you want to do it. So somebody might make a recommendation not particularly understanding something, and so maybe they shouldn't all be followed. But there are some that they just go nowhere. There's no way really to tell. So it can be literally instant to months to years to never. Up there. Got a couple.
Hello, can you hear me?
Yep.
Yeah. Thank you very much for your wonderful presentation. I'm a faculty member at the University of Tennessee Department of Nuclear Engineering. Mm-hmm. And as you probably know, we support many programs, including nuclear nonproliferation and safeguards, among several other areas, materials, etc. Recent times, as you know, the low cost of natural gas appears to be promoting the closure of many nuclear power plants around the country. And is the Academy at all looking into the erosion of nuclear programs due to this?
There have been a
shift in
lot
energy?
of studies that have been done over time around the role of nuclear power in the grid, et cetera. There are no studies being undertaken right now. I mean, I personally agree with your assessment. It's been very interesting, though. Once a nuclear power plant is paid for, it really becomes dirt cheap. So, having lived in New Mexico, and then living in California, and now I live in Northern Virginia, and if I look at when I first moved to Virginia, I said, there must be something wrong. My electric bills are way too small. I don't get why my electric bills are so small. So I did a little bit of digging. What I found is that Dominion, who's my power company, is 41% nuclear, with reactors that have been already depreciated, 46% gas, 10% coal, and a few percent renewables. It's hard to beat the cost of nuclear power once it's actually in place. So I'm a personal benefactor with $33 electric bills running an air conditioner in a 3,000 square foot house because of nuclear power. And you're not too bad here. I don't know what does your power come from TVA?
Yes.
What percentage is TVA nuclear? Do you know? I don't know what the answer to that is. 40? So you're probably pretty cheap here. And you have a lot of hydro, I think, here too, don't you? So you're probably relatively cheap here. It's interesting. Dominion actually, in fact, Dick Meserve is one of our counselors, our board members, who used to run the NRC, was one of the commissioners. And I just recently asked him exactly that very question. And I said, Dominion is still actually ongoing with the licensing process for 2 plants. And what he told me was that, well, you go through a licensing procedure, and once it's licensed, and you may know the answer to this, but that license has a lifetime of some pretty good chunk of time. And it's cheaper for Dominion to go ahead and finish the licensing procedure and not build than it is to stop and try to restart the licensing process. And I think they're waiting to see what happens to the price of natural gas to see whether they want to build other plants or not. But there's this whole big debate about what do you do. I mean, you've opened a real giant Pandora's box of this. There are lots of studies going on about the reliability of the grid and the resilience of the grid. That's broader than just nuclear power. So, for example, with our current architectures, if a grid is more than about 30% renewables, there's real stability problems, right? So you need something to carry a base load. Well, gas is pretty reactive. You can ramp gas plants up and down pretty quickly. Nuclear reactors not quite so quick. But nuclear makes a great base load for things. So there are studies being done that say as we get into more renewables and we want to worry about base load, what's the role of nuclear power in that base load? So those things are in fact being considered. So maybe not specifically gas versus nuclear, but the notion of how nuclear fits into the larger issue of how you maintain a grid, especially as you increase renewables. Those things are actually being looked at right now. There's at least 2 studies I can think of that are ongoing that are going to touch on that. I saw another hand up there, I think. Did I see another hand? No? Okay.
Well, I think this could go on, but I
Okay.
think we should try to wrap it up. I want to take this opportunity to once again thank you very much for visiting.
Oh, thank you so much. There it is. So this feels like leaded glass. I think I need to put it between the reactor and me. Why don't you hang on to it and we'll get it packed up.
Thank you.
Thank you all for coming, and good luck.